want to begin by sharing my screen. Let me just, and also getting everything organized so I can use my screen. Whoops. Sorry about this. I want to get to, okay, I'm experiencing some technical difficulties. Hold on. There we go. Can you see my screen now, folks? Yes?
Yes.
Very good. Thank you so much. Well, again, welcome colleagues to the fourth of 4 lectures on program effectiveness research. Since some people have not attended all, and just as a matter of, reporting what we have discussed and what we're going to discuss, let me refresh your memory that lecture 1 was about how program effectiveness research is grounded in program logic models and how those models shape the research questions that we ask as we conduct program effectiveness research. In lecture 2, I moved to research designs and the various ways in which program effectiveness research seeks to create treatment and control groups and use counterfactual reasoning to explore program effectiveness. Lecture 3 discussed how to estimate various kinds of causal effects of a given program on outcomes and also on implementation processes. And today I'm going to discuss how to report about the program impacts that are being estimated through research. So again, just a reminder about the nature of this lecture series. I cover many topics in each of these lectures, and no topic is covered at a level of detail that it really requires. In fact, many of the topics covered today could easily be the topic of their own lecture or even lecture series. But the point is not to cover topics in detail here. What I am trying to do is point attendees to areas where they need to gain deeper knowledge. And so to assist attendees, in addition to the lecture, I point at the end of my lecture slides to various resources, places that people can read about the topics I discussed today. And those readings generally have pretty good reference lists that can help you deepen your knowledge. So today is not about, deep understanding, it's a roadmap. As in the previous lectures, I'm going to limit audience participation. I expect to lecture for about 90 minutes today, and then I'm going to break for Q&A session. If you want to ask me a question during the first 90 minutes, hold it until that break point and then use the Q&A function on Zoom to post your questions. And please hold your comments to all in the chat box because that pops up on my screen and I'm reading slides. So today I have 3 goals. First, I'm going to review some common problems in program effectiveness research, and I'm going to talk a little bit about how you can address these common problems in research planning and reporting. And this is basically designed to acquaint attendees with some technical terms that get used in discussions of research quality and relevance, particularly with respect to rigorous program impact studies. So the key terms that I'm going to discuss today are study pre-registration, the problem of generalization, in which I'm going to define an inference population in a sample and talk about how to generalize from sample to inference population. I'm going to discuss statistical power and how to do power analysis. I'm going to discuss confirmatory versus exploratory kinds of analyses, what the difference is and why that's important. I'm going to discuss sample attrition. including general attrition from a sample and differential attrition, and I'm going to discuss how that can sometimes erode what's known as baseline equivalence. So these are sort of main topics that need to be reported on when a rigorous impact study is being conducted. Then in the end, I'm going to provide a simple outline of the topics that are getting covered in reports, and hopefully, because I have presented this lecture, you will be able to understand what exactly goes into these categories. And I won't cover them now because we'll be listing them at the end of this lecture. So let me make a quick bridge from previous lectures to today. You'll recall in lecture 2, we described research designs that define clear treatment and counterfactual conditions through the use of treatment and control or treatment and comparison groups. And we also classified these designs in terms of their ability to produce warranted causal inferences about program impacts. So warranted causal inferences, we argued, were possible only when assignment to treatment was independent of variables that affect outcomes. That is, there is no confounding. And today I'm going to show you how to address the possible confounding going on in any real study by reporting about baseline equivalence. Recall, I also, in lecture 3, defined different types of program effects that get estimated with designs that have treatment and control groups. I defined the average treatment effect. I then modified that to be represented as an intent to treat effect or a treatment untreated effect, depending upon the compliance analysis. And I further talked about how you might want to estimate conditional average treatment effects. Today, I'm going to discuss a different way of thinking about treatment effects that's related to the problem of generalization. So here, I'm going to make a distinction between a sample from which one derives a sample average treatment effect, and then inference population, that is the population to which we want to make an inference about a population average treatment effect. And then I'm going to show you how the presence of conditional average treatment effects can make sample average treatment effects differ from population average treatment effects. And that's how I'm going to define the problem of generalizing from sample to population. Further, recall from lecture 3 that while we defined different program effects conceptually, we didn't really discuss much how to formally test whether a program effect was statistically significant. So today I'm going to touch upon this problem briefly, but in several different ways. First, I want to discuss the problem of specifying the statistical hypotheses that are going to be tested in your study in a document that is pre-registered and placed in a repository. Then I'm going to show you that the ability to test a statistical hypothesis depends on the statistical power of the test. And I'm going to show you here that statistical power is largely related to sample size. And I'm going to show how that relationship can be affected by clustering, or this is really the multi-level data problem that has come up in previous lectures. And finally, I want to show you that when you're testing multiple statistical hypotheses simultaneously, you're going to need to control for family-wise error rates or false detection rates. So let's just briefly have some background on today's lecture. It turns out that if you read the literature on the quality of social science research in general and program effectiveness research in education in particular, there are deep concerns about the quality of that research. And these concerns revolve around several different kinds of issues. One is that program effectiveness studies in particular tend to overuse small convenience samples. And these samples tend to lack adequate statistical power and also make it very difficult to generalize from the sample average treatment effect to the population average treatment effect that you want to make an inference about. Second, there's a tendency in all of social science research and even broader research in biomedical sciences and beyond. There's an overuse and misuse of statistical significance testing, especially in exploratory analyses. And so that's a problem I'm going to talk about today. And then there is, in many intervention studies, a failure to provide descriptive information, either about the program that is actually under study or how it was implemented. And I want to discuss very briefly how and why that is an important topic to cover in reporting. So these concerns that I just discussed have led to really three significant movements that you should be aware of, both in general social science research and in education research. The first is the move to pre-register study designs for public inspection. The second is a move to setting standards of research quality so that when people read studies, they will know which studies are high quality and which are not. And the third is a move towards setting standards for research reporting so that readers can surface the information that's needed to make a judgment about quality from a research report. Now, the problems that I'm mentioning here surface at various phases. So early in studies, researchers often specify their statistical hypotheses in advance. As they conduct the study, they often select small convenience samples that makes it difficult to generalize. They often use research designs which allow for high attrition or fail to collect complete data. They often, in the analytic phase, do exploratory data analysis, or what in my shop we call fishing expeditions. There is often a tendency in the reporting phase to be selective in reporting of the results, to cherry pick the results that are favorable to an intervention program and to suppress results which may not be favorable to the program. And in the post-reporting phase, there's a not sufficient emphasis on replication and extension of findings. And so people have been talking about this in various ways to address these problems. To address the problem of failure to specify hypotheses, people increasingly emphasize the need to pre-register study designs and to specify which hypotheses are going to be tested. With respect to the small sample problem, people have emphasized the need to define an inference population, to choose a sample that represents that population, and to conduct power analyses to determine an appropriate sample size for a given study. Because attrition and missing data are so present, people insist now, most reporting standards insist that researchers conduct, analyze, and report on overall and differential attrition and on baseline equivalence. So we'll discuss that problem. On the exploratory data analysis problem, I want to describe how to prevent the kind of fishing for positive results by following a pre-registration plan, and how in the reporting phase not to publish only positive findings and suppress negative findings, and how as a matter of transparency to provide the public with both your data and the analytic scripts you use to analyze it. And I won't talk much about this, but in the post-reporting phase, it's important for people to value replication. You'll see when I talk about significance testing why replication is important. So this leads to the topics I'm going to cover. I want to talk about pre-registration. It's a phenomenon many of you may not have heard of. So what is pre-registration, and how can I do this? I want to talk about sampling and generalization, clarifying what I mean by an inference population, talking about how to sample from that, and talking about how to generalize from your sample to your inference population. I'm going to talk about power analysis. I'm not sure the extent to which attendees have heard about this, so I want to talk about just very briefly what statistical power is, how it varies, and how you can calculate it for a given study design. I want to talk about group equivalence, the assumption that there are no confounders that are operating such that we can make a clear causal inference or a warranted causal inference about program effects is demonstrated by group equivalence. And so I want to talk a little bit about the group equivalence problem that's related to the attrition problem. So I want to talk about different kinds of sample attrition, how to calculate it, and when you should worry about it. I'm going to talk about statistical hypothesis testing, the difference between statistical and practical significance. And I'm going to talk about a couple of practices you may or may not have heard of called p-hacking and harking and how to avoid those practices. And finally, I'm going to touch very briefly on service delivery and implementation analysis. I'll also touch very briefly on why it's important these days to make your statistical code, your data publicly available. And then I want to talk about the content of a final report. So a big set of topics today. We've already gone for 25 minutes, so let's just race through these topics. We'll begin with the pre-registration problem. So you may or may not know that pre-registration is required by law in the USA for any clinical trial conducted in the biomedical sciences. And in fact, there's a very widespread movement in the social sciences generally, political science and psychology in particular, to pre-register study designs and place them in a repository. Now, the idea is that if you pre-register how you are going to conduct a study, you've created safeguards against various research practices that can potentially produce misleading findings. And so increasingly, social science journals are accepting pre-registration reports and indexing them. And they are also noting when they publish papers whether or not the research upon which the publication is based was pre-registered. So you may encounter a journal that you're submitting to that has these kinds of policies. Moreover, there are an increasing number of study registries that have been created, including registries germane to educational effectiveness studies. So if you're thinking about registering a study, the easiest place to register is the Center for Open Science. But if you are interested particularly in educational effectiveness studies, you can pre-register your study design in the Registry of Efficacy and Effectiveness Studies in Education. So what's in a pre-registration entry? General study information. Who are the PIs? How was it funded? What intervention is being studied? When was the study going to be conducted? A description of the study. What kind of intervention are you studying? What are the treatment and control arms? What kind of schools are you going to be doing? Where is the study going to be conducted? And what are the treatment and comparison conditions? Then you list the confirmatory and exploratory research questions that you are going to explore in your study. You then describe the study design, the sample characteristics, the outcomes that you are going to analyze, the plan you are going to use to analyze those, and any additional materials you wish to attach. And study plans of this sort often have addendum and are revised. So that's a brief discussion of what's in a plan. And I have referenced for you at the back of this lecture slides two examples of, or an example of a study pre-registration. So pre-registration forces you to specify your design and the research questions in advance of conducting your study. And because you do that, you are not, the reader of a study knows that you followed a plan and did not engage in the kind of fishing and censoring of the material so that you only are providing positive results, not negative results. So pre-registration is important, and I would encourage those of you who want to do impactful research at scale to pre-register your studies. So now let's talk about the problem of sampling and generalization. So any registry, and in fact, any good study, are going to include a description of the sample of the study, the units that were in the study. The question, of course, is what aspects of the sample am I going to describe? And the answer to that question comes from your answer to the following question. What is the population to which I want to generalize my findings? And the population to which you generalize your findings, I'm going to call the inference population. And defining this inference population is the first step in reporting about your sample. Now, I'm also going to talk a little bit about what it means to generalize from a sample to a population. And so let me just talk for a brief moment about that. Recall that we have discussed the goal of program effectiveness research is estimating an average treatment effect. Now, we also discussed random assignment and how random assignment assures that treatment and control groups are equivalent on pre-treatment covariates that affect the outcome. But in fact, random assignment is not the same as random sampling from a population. And in fact, random assignment as a procedure is silent about the kinds of units that actually compose your treatment and control group. So in many cases, the sample of units randomly assigned to treatment and control in a study are not selected to be representative of some larger population, but are rather selected simply on the basis of convenience. They were easy to recruit, they had formally cooperated with you, they are within a certain geographic region that you find convenient to sample from. And so that makes it a problem when researchers want to generalize the results of their sample, their estimate of tau average from their sample, and say it is what could be expected in some broader population, because what you have is a convenience sample, not a disciplined sample of the broader population, the inference population to which you wish to generalize. So the question for research planning is, how can I reasonably generalize from the sample estimate of program effects to what could be expected in the population? Well, that requires us to define two groups, a study sample and an inference population. And using that idea, we define two treatment effects, a sample average treatment effect, the effect we estimate using our sample, and the population average treatment effect, which is the effect we really want to know about, and the information we have about it comes from our sample average treatment effect. Now, the question is whether you should worry about whether your sample average treatment effect is a good guess about what the population average treatment effect is. And the answer is these two estimates will differ if there are conditional average treatment effects in the population. That is, treatment effects vary across subgroups in your population, and the distribution of subgroups differs in your sample versus the target population. If I had a representative sample, I could say my sample average treatment effect is likely to be the population average treatment effect. If, however, my sample is very different from the population I wish to make an inference about, and there are conditional average treatment effects in the population, then the sample average treatment effect is likely to be very different from the population average treatment effect. So how can I do this? You begin the process of generalization by defining an inference population. Well, like, how do I do that? Well, here's some possibilities. You could define the inference population as all units likely to enroll in a treatment. So this is a useful definition when the enrollment in a program is voluntary. For example, the program is sold in an open market, or participation is discretionary and a matter of choice by the units. On the other hand, you could define the inference population as all units for which treatment is indicated. So this definition is useful if, for example, an intervention is targeted for use in a specific population. This is an intervention designed for high poverty schools, or schools with a history of low achievement. That would be specifying the inference population by units for which treatment is indicated. On the other hand, yet a third definition might be all units in some geographic region or political jurisdiction. And this definition is useful when an intervention is politically mandated or has general relevance. And so there is no single definition of what an inference population is. It depends upon your choice, and you have to be disciplined in your choice. But once you have defined an inference population, there are three main strategies to generalize from a sample to that inference population. The first and least assumption laden, and probably most preferred, but often beyond the resources of any given investigator, is to use a disciplined sampling and recruitment strategy to create a representative sample of units that are going to be assigned to treatment and control. So this is an attempt to mirror in your sample the characteristics of the inference population. Now, often, because people are using convenience samples, they don't engage in this kind of systematic and representative sampling. So a second approach, if you don't have a representative sample, is to assess the similarity between the study sample and the inference population, and then adjust the estimates for these differences. Now, I'm not going to recommend this, nor am I going to talk about this, although I have a reference about this. This is a quite difficult analysis, requires a lot of assumptions, and it probably is beyond the scope of most investigators. The third approach, however, is simply to describe the population represented by your sample, and then provide readers with a sense of how different your sample is from that inference population, and give them appropriate cautions. That's the approach that I'm going to describe now. So the simple method that I am talking about begins by reporting how the study sample differs from the inference population on specific variables. And the variables that you're going to select are variables that you suspect might be moderating the program effect. That is, you might think that there are some subgroups in which this program works well and some in which it doesn't work well. Then you want to include those as variables to compare your sample and the inference population. And so for each of these potential moderators, you just create a table that has some data, descriptive data about each of the variables. And then you focus on specific variables where there's a high standardized mean difference between the sample and the population, and you report those differences to your readers. So those reports might read as follows. Compared to schools in the inference population, schools in the study sample were more likely to be located in smaller school districts, serving communities with lower incomes and higher percentages of white versus minority students. So you just provide some information about the differences between your sample and the inference population. There is a more sophisticated way. I think most of you can do this because software exists to do this. And that approach is going to generate a single coefficient of how different your sample is from the inference population. So once again, you specify a list of variables that you suspect might modify the treatment effect. Then you collect data on those variables for your inference population as a whole and for the sample which you drew from that population. Then using those data, you estimate the probability that a site in the inference population was actually in your study. And so in essence, what you're creating is a propensity score for being in your study based on these covariates. Then once you have that propensity score for each unit in the inference population in your sample, you can plot how different the two groups are on this propensity score. And that and so there's a graph showing you the dotted line and the main line, and you can see that these distributions are in fact different. There's a different mean for the study sample than there is for the population, a bit of a different skew. And you can actually calculate something called a generalizability index, or B index because it's beta. And this index varies between 0 and 1. And so using that, you can provide your reader with some information about how different your sample is from the inference population. So if the index of this generalizability coefficient, or B, is 0.90 or above, you could, for example, say to your reader, the sample I have in my study is as similar to the inference population on potential moderators as a random sample of the same size would be, and therefore the sample average treatment effect is likely to be similar to the population average treatment effect. If, on the other hand, that value is between 0.5 and 0.9, then you would inform the reader that the sample differs from the inference population enough that if moderators are present, the sample average treatment effect will likely differ from the population average treatment effect. And so you give them the cautionary language there. And if that index value is below 0.5, then you have to report that the sample is very different from the inference population and does not include certain kinds of units present in that population. Therefore, the results of this study can only be applied to units like the ones included in the current study. So it's very important in thinking about generalization to examine the differences between your inference population and your sample, and I've given you some methods for doing that. Now, let's suppose that we have thought carefully about our inference population, drawn a sample, discussed the generalizability of it, or have given some thought to how we would do that. The next step is to calculate and report on the statistical power of your study design. So I want to talk about that for a moment. Recall that we defined the estimate of interest in a program effectiveness study as tau average, the difference in means of the outcome variables across treatment and control groups. So when you are listing your confirmatory hypotheses in your registry entry, the question will arise as to whether, or your hypothesis might be explicitly, almost always will be, whether this difference as estimated in the sample is statistically significant from zero. And then, that hypothesis is generally tested using the null hypothesis testing framework from statistics. The null hypothesis is that tau average equals zero. You conduct a statistical significance test to calculate the probability that the observed value of tau average differs from zero by chance, and we typically want that probability, alpha, to be 5%. So statistical power is defined as the probability that your statistical test with a given alpha searching for a given effect size correctly rejects the null hypothesis when that hypothesis is false. That's the definition of statistical power. And typically researchers want power to be equal to 0.80. That is, they'd like to have at least an 80% chance of detecting a statistically significant effect when that effect really is different from zero. So why is statistical power important? Well, having adequate statistical power helps prevent false negatives from being discovered. That is, the declaration that a program is not effective when in fact is, simply because you failed to reject the null hypothesis after statistical testing. And so I want to talk now about what determines statistical power. And the usual answer is that statistical power is a function of sample size. But what I want to show you is that how big a sample you need to obtain adequate statistical power depends actually on several factors and varies by the kind of design you're using for your research. So when the outcomes of the units in a sample are independent, that is, the subjects that are the subjects of study aren't chosen from clusters like schools or classrooms or neighborhoods where there are group level effects on the outcomes. Statistical power, when the units are assumed independent, depends on sample size. It also depends on the true absolute size of the effect. It depends on the variances in outcomes within the treatment and control group, and it depends on the level of statistical significance that you set for your hypothesis test. So if you're doing one of these studies where the units are independent, there are any number of power calculators you can use to plot statistical power. And I generally use a little program called G-Power. Very powerful and interesting little program, and I have a reference about that. So the next slide is going to show you a power curve so you know what I'm talking about. So in this graph, what you see is the number of observations is on the horizontal horizontal axis. The vertical axis is statistical power. Recall, we usually by convention want power to be 0.80. And the first thing you'll see is that power is a function of the effect size you want to detect. So if you look, the green line is a researcher interested in trying to detect a very small effect, standardized effect of 0.20. The middle line has a bit larger effect, and the top line is a huge effect. And so when you look at these graphs and how power improves with the number of observations, you'll notice that power is always greater when the effect size you're attempting to detect is greater. But holding that constant, you'll notice it's a function also of sample size. Now, the problem of statistical power and sample size is much more difficult when you have clustering in your data, and clustering is omnipresent in education research. So I'm going to just briefly discuss power and sample size calculations when there's clustering. So many times in education, the units that we want to study, say students, are clustered within schools. And often what we do is we assign the treatment to schools, but we want to study the outcomes for students. And so this is called a cluster randomized trial, where the treatment is assigned at the school level, but the outcomes are investigated at the student level. In this kind of study, which is very common, it's going to be very common in education research, we can't assume that the outcomes of the units are independent of each other. In fact, there are school effects present. And as a result, in one of these cluster randomized trials, power is going to depend once again on the p-value, once again on the effect size to be detected. But the sample size problem is how many clusters, for example, schools are in your sample, and how many subjects are within each cluster. That's within each school, how many students. Power is also going to be a function not of variance among children, but variance among schools, and then a number of other factors that I'm not going to discuss. So let me just quickly show you how this works and let you in for a surprise. Cluster randomized trials that are aiming to achieve a power of, say, 0.80 often require as many as 50 or 60 schools. So here's a very simple power curve that shows that we don't really get power of 0.80 until we have about 45 schools. But and it shows you how power on the horizontal axis improves as I add schools to my sample. But this current example assumes that the number of subjects per school is 20, that the intra-class correlation, or the percentage of variance in the outcome of interest that lies among schools, is 5%, that I'm trying to detect a pretty small effect size of 0.25, and my alpha is going to be 0.05. So under those conditions, it takes me roughly 46 schools, half assigned to treatment, half assigned to control. And note also that after I add about 60 schools, I'm not really improving power. So one thing that's useful about a power analysis is it'll tell you what the sweet spot of sample size really is. Now, I told you that power actually depends on a lot of things. Note here that power declines as the intra-class correlation increases. So what you see here is, again, power on the horizontal axis. This time, the percentage of variance lying among schools in the outcome variable. And what you see here, we assume, once again, here I'm fixing alpha to be 0.05. I'm going to say, okay, I have 50 schools with 35 subjects each. And I'm going to look for an effect size about 0.30. What you see is that design has sufficient power when there's very little variance among schools. But if there's a lot of variance in the outcome among schools, it's not a very powerful design at all. Okay, and so that's a very big concern. Then I want to show you that, contrary perhaps to what you might think, in a multi-level study, power can increase by the number of students you have in a school, but not nearly as much as it improves when you add clusters or schools to your study. So this graph, again, has the number of students per school, and it's assuming you have 40 schools. It's assuming a alpha of 0.05 and 20% of the variance lying it's assuming about 15 or 5% of the variance lying among schools. There's two curves there. But the point is, adding subjects to each cluster does increase power. But again, if you look at this, and we know from experience, it doesn't add nearly as much as adding clusters to your study. And adding subjects to each cluster provides bigger increases to power when the ICC is smaller. And so the reason for this, and the way to think about students versus schools as adding to power, is this: when there's strong clustering, the information added from a single student within a school is much, much less than the information gained by adding a school. So finally, you've seen that power depends a lot on the amount of percentage of variance among schools. One way to reduce the amount of variance lying in the outcome lying among schools is to control for pretreatment covariates that predict outcomes. And if you do that, the more you can explain between school variance, the more power you will get. And this slide will show you how that happens. But that's some considerations about power. Now, one of the things about statistical power that I have learned in my day is that it requires a lot of assumptions, and it's very complex. And so I always recommend to people who are doing power analyses to begin by using existing software, and there's plenty of software available. So when you get this software, it's going to ask you a number of easy questions, like what's your preferred p-value? And so, by convention, p equals 0.05 one-tailed test. And it's pretty easy to choose a standardized effect size. Either I'm looking for a small effect, 0.20, or a medium standardized effect, say 0.40. But the software is also then going to ask you to input values you might not know, like what is the percentage of the variance in your outcome that lies among schools? Or what are the variances in treatment effects? Are there conditional average treatment effects, and more? And those questions are not matters of choice, they're matters of empirical fact. And so to get plausible values for those inputs into the program, you actually have to search existing research or estimate it from some existing database, not the study database, but another database. So importantly, also study designs, but different power calculators are useful for different designs. And so I have listed here some places you can go to look at power calculators and choose one that really makes it easy for you to estimate power given your study design. Now, the question, of course, because this is a lecture about reporting, is when do I report my power calculations? I report them in the pre-registration phase of my work because I want to demonstrate to people that I thoughtfully attended to statistical power as I designed my research. You want to report it in your funding applications because people do not wish to fund underpowered research. And you report it in your final and published reports, especially if your study was pre-registered. And that's because if your study was theoretically powered to detect an effect of a certain size, and you didn't find that effect, and you're reporting that you didn't find that effect, you can at least argue that your failure to reject the null hypothesis was not due to a lack of statistical power. Now, sometimes people will be asked to report post hoc or after the fact power calculations for the reasons listed in this slide. I don't recommend that. Okay, so we've talked about defining an inference population, selecting a sample, how the selection of that sample has to represent the inference population and be of sufficient size to be able to detect an effect at the level of statistical significance and effect size that we desired. But now I want to turn to what happens as the study goes on, and that's the problem of baseline equivalence. So what is baseline equivalence and why is it important? Well, recall that a credible causal inference about tau average depends on the assumption that the treatment and control groups are equivalent across all possible variables that might affect outcomes. Now, ordinarily, we don't have an exact list of all these potential confounders on which treatment and control might differ. There's no way. We don't have, there could always be some unobserved thing that we didn't measure that's confounded and could have an effect on outcomes. That's why we do random assignment, because it increases the chance that the treatment and control group will not differ on not only observed covariates, but also unobserved ones. However, sometimes random assignment doesn't guarantee that the treatment and control group are in fact equivalent on all confounders. After all, random assignment capitalizes on chance, and with smaller samples, there's especially a chance that randomization actually failed to make the two groups equivalent on these confounders. So baseline equivalence is a term that means that the treatment and control groups have been found to be equivalent on a set of observed variables that were measured prior to service delivery, and that prior research has found are potential confounders. And if the treatment and control group are not equivalent on these observed baseline covariates, then the validity of the causal inference that you're reporting is questionable, because it might not be that treatment and only treatment accounts for the differences in observed outcomes across treatment and control groups. It might be that some of the effect you are observing is due to differences in pretreatment covariates. So most rigorous research will assess and report on baseline equivalence. And this involves several steps. First, you consult research to establish the important baseline covariates that might affect the outcomes you're studying. You then obtain measures of those covariates for both your treatment group and your control group, bearing in mind that these are measures that are taken before treatment services are delivered in your study. You then calculate the means and standard deviations of these covariates, both for your treatment group and your control group. You then take the standardized mean difference in these covariates across the treatment and control groups, and you report those data, and you report them in a table in your final report. Now, the procedures for reporting this are going to vary depending on whether you implemented random assignment or a quasi experiment, and whether or not the outcomes are clustered or not. So let me just talk a little bit about that. So when you are doing a randomized controlled study where the individuals assigned to treatment and control, the outcomes are independent of each other, the What Works Clearinghouse in the United States, which is a government funded agency that rates the quality of research, provides the following guidance about how to interpret and act upon findings about a lack of baseline equivalence. So in this table, what you see is we have across a list of variables the standardized mean difference. And what the What Works Clearinghouse is telling you is if there are standardized mean differences between treatment and control group of a certain size, then you need to make the reader aware of that and perhaps take some steps in light of that. So if the absolute value of the difference between treatment and control on any covariate is always less than 0.05, the What Works Clearinghouse and most people would consider you to have samples which are substantially equivalent on baseline covariates. When you find differences that are between 0.05 and 0.25, the What Works Clearinghouse, and I think a lot of researchers would recommend that you use statistical adjustments, which simply means that you now estimate treatment effects in a multiple regression framework where where outcomes are predicted not only as a function of treatment, but also the covariates where the samples, the two groups are uh, non-equivalent. And finally, if you're finding effect sizes differences greater than 0.205, standardized mean differences on covariates known to be confounders greater than 0.25, your study is verging on not being a particularly trustworthy study. That's the What Works Clearinghouse guidance. The situation is a bit more complex in cluster randomized trials in the following sense. Here, we're assigning treatments to schools, and so we want to see baseline equivalence on pretreatment covariates at both the school level and then at the student level. So to do that, what you're looking at is think about confounders at the school level that might predict average differences in achievement among students. And those would be like the percentage of children in poverty attending a school, the percentage of minority or non-native language speakers or non-standard language speakers. And so first you look at those mean differences across schools, then you look at the covariates that operate at the individual level that might be affecting your outcomes, and you analyze the standard mean differences there. And large differences at either of these two levels requires you to use the procedures that the What Works Clearinghouse has described. In quasi experiments, you are often matching on these covariates in the first place. And so, here the matching, as we discussed, is to find important baseline covariates to match on them. And usually after matching, you won't find differences in baseline equivalence. You will find baseline equivalence, unless, of course, your matching process was somehow horribly flawed. And so to prove to the reader that your matching process wasn't horribly flawed, you present the baseline equivalence between the matched groups. And generally that should work out to be good if your matching was good. So we now have defined our inference population, chosen a sample of sufficient size to detect effects, shown that after sampling, the two groups are equivalent on baseline covariates. I would now like to discuss the problem of attrition. So you have a recruited sample and you assign them to treatment and control groups. And as the study begins, because you've been a good researcher, they're often, they're often equivalent samples on these baseline covariates. But in any study that I have ever conducted, and any study that most people conduct, some subjects drop out of the study. And that's the problem of attrition. So here's an important point. If you collect outcomes data from the dropouts and the people who are still in your study, there isn't any study attrition, and group equivalence is maintained across the study period. The problem comes when you don't collect data on outcome from the units that have dropped out of your study. Then you have attrition. And if there's attrition in your study sample and it's high, then you might not have samples, analytic samples, that are equivalent on confounders, and this can bias your estimates of tau average. So since attrition is a threat to valid causal inference about treatment effects, researchers should always report on attrition. And this involves calculating overall attrition and differential attrition. And so there's a handy graphic for how to do that. You'll notice that there is overall attrition and there's differences in attrition across the two groups. And what I want to do now is show you how to think about whether or not your study has been compromised by attrition. So the reason we're concerned with attrition, even after we have shown baseline equivalence, even baseline equivalence with our attrited sample, is that all we have to judge equivalence is observed variables, but there could be unobserved variables. So you could have equivalence on observed variables, but there's always a threat that there are unobserved variables that are not equivalent and that were somehow associated with attrition and are therefore biasing your study. So the What Works Clearinghouse has a set of standards for judging the quality of research by attrition. And I won't talk now about the difference between the conservative standard or the liberal standard, but what these show you is that any study that has low overall attrition can still be problematic if there are high rates of differential attrition. And any study that has high rates of overall attrition can be okay if there's little differential attrition. So that's the way to think about and report on attrition. And so I'm going to move now to the estimation of effects given your sample. But here is the review. We've defined an inference population. We've chosen a sample to represent that population. We have made sure that that sample is of sufficient size. We have allocated the sample to treatment and control. We checked for baseline attrition before the study began. We then checked again for baseline attrition, only this time we used the analytic sample, and we report the rates of overall attrition and differential attrition so that readers can think carefully about whether there are unobserved covariates that might be confounding. Now we're ready to estimate the treatment effect. Okay, so the typical study is going to report a number of things about what I have been calling tau average, the treatment effect. It might report differences in outcomes across treatment and control as an intent to treat effect, or that's the simplest and mandatory reporting requirement. It might assess conditional average effects. It might look at service delivery or contrasts across treatment and control. You might be engaged in estimating mediation effects. Whatever effect you're reporting, there's two ways to report the findings about effects. One is to report an effect size. So in our case, we are, let's say we're estimating the intent to treat effect. It's the simple mean difference in outcomes between treatment and control group expressed as a standard mean difference. Okay, that's one way to report an effect size. You may know that as Cohen's d, for example. Or you can also report the statistical significance of that finding. That is the p-value of this test statistic you use to determine whether or not the difference in means was different from 0. And normally a researcher actually reports both types of effect metrics. And the question here is how to do that responsibly. So it turns out that there's some controversy about the reporting of p-values versus effect sizes. And mostly the controversy revolves around reporting p-values, not effect sizes. So the problem, as we have seen from our discussion of power, is that many large effects that you find won't be statistically significant if your study lacks statistical power. Alternatively, you can find many small effects which are not particularly substantively important, but you can find that those are statistically significant if your study is highly powered. So one should not confuse the size of an effect with its statistical significance, and you should report both effect metrics. Okay, so the second thing that makes p-values controversial is they are in fact highly uncertain statistics. And I will discuss that. And they are also subject to what's known as p-hacking, which I'm going to discuss also. So let's talk for a moment about the uncertainty of p-values. That is, okay, the effect was significant when alpha was set to be 0.05. That's the p-value issue. The p-values are often calculated based on test statistics that have unwarranted distributional assumptions. That's not a difficult problem to solve. Instead of using sort of parametric T and F tests, you could go to using randomization or permutation test statistics, which have fewer distributional assumptions. That's not the issue here. The issue is even when distributional assumptions are met, p-values are sample specific. They express the probability that an estimated effect is different from zero given your sample. So if we change samples, we're very likely to get a different p-value for exactly the same effect. So p-values for the same effect can vary markedly from sample to sample. Second, and just as an example of this, and I give you a paper that shows you how this works, the 95% confidence interval for a p-value of 0.01 is 0 to 0.54. So in a lot of cases, the same effect would not be replicated at the level of statistical significance if I chose a different sample. On the other hand, if I set a very stringent p-value, say 0.0001, then the 95% confidence interval is between 0 and 0.05, and that's a much more tolerable level of uncertainty of this test statistic due to sampling. And so another example is two studies, each powered at 80%, only have a 64% chance of both finding that an effect of the same size present. So there's a ton of variability in p-values even when the effects are the same, because p-values depend on and are sample specific. And that's an important thing for you and the reader to understand. So given all of that, here's my advice for how to report effects in a good study report. First, always begin by reporting the effect size as usually some kind of a standardized mean difference or standardized effect size, and the 95% confidence interval for that effect. Then you start by interpreting how large that effect size is before you report statistical significance. Then always report the actual p-value, not whether it exceeded some arbitrary threshold. And that's because we know that some p-values are more likely to be replicated across samples than others, and p equals 0.05 is not really likely to be replicated across samples. Remember that p-values are sample and power dependent, and make sure your reader understands that. So you would consider, for example, discussing the power of your study as you reported it in your pre-registration plan as you discuss the p-values. So what are some possible ways to discuss results in your reports? Here's one way. We found a medium-sized effect of the treatment on outcomes, Cohen's d equals 0.4. But this effect only had a 75% chance, p equals 0.25, of being statistically significant from zero given our sample data. Or we found a small effect of the treatment on outcomes, Cohen's d equals 0.10, but this effect had a 97% chance, p equals 0.03, of being different from zero given our sample data. Now you are making the reader aware of both the effect size and its statistical significance, while reminding them that the statistical significance effect is sample specific. Okay, so now let's go to using statistical significance and the p-hacking and harking problems. These are really another area that people have been talking about. And this practices I'm about to describe is one reason why people are especially interested in pre-registration. So let's define these terms. P-hacking, as it's used in the literature, is a process of using exploratory data analyses to discover statistically significant effects in your data. But these effects, because you're exploring so extensively, are very likely to be sample dependent. So in particular, if you set P at 0.05 and conduct many different analyses using the same data set, you're almost always going to get a set of findings that are statistically significant, but that's only because of chance, not because you've discovered a real relationship among two variables. And p-hacking is often accompanied by what's called harking, hypothesizing after results are known. This is the notion that you find some significant effect, and then you justify why that effect was found, when in fact, you never expected to find that effect. Okay, that illustrates the difference between a confirmatory hypothesis and an exploratory hypothesis, and why confirmatory hypotheses, which are specified in advance and usually grounded in some reasonable body of research and theory, are better than these exploratory findings with after the fact theorizing. Now, both harking and p-hacking are really been criticized in the scientific literature. And again, they're the reason why we ask for pre-registration, in which we specify in advance the hypotheses to be tested, so we know that they did not result from p-hacking. So there are various ways in which you yourself might actually be guilty of p-hacking and harking. For example, you might think, oh, well, I'm just estimating a simple ITT effect, the difference in means between treatment and control. No, there's nothing going on here. How could I p-hack? Well, one way this occurs is, and you see this, researchers often collect multiple outcome measures. And sometimes you find that your treatment effect is present on some outcomes, but not all outcomes. And so a p-hacker reports only the data for the outcomes where a statistically significant effect was found and suppresses the negative effects, whereas the ethical researcher has specified what outcomes are going to be studied and provides the full data on outcomes. We've seen also that sometimes your analyses of effects require you to use covariates to control for various confounders. Well, this is a legitimate practice. It can improve the precision of your estimates, and it can be used to control for baseline equivalence and attrition. Okay, it's a legitimate practice. However, if you start fiddling with the covariates that are included in your outcomes model, and you test many different versions of the regression equations, sometimes it has these covariates, sometimes it has those, and you find that under one of these models, you got a statistically significant effect, that's p-hacking. But the responsible researcher has specified in advance which variables will be or potentially will be included, any variable upon which baseline equivalence has not been shown, or these variables have been shown to improve precision, you specify in advance in your pre-registration entry, then we know that the result being presented is not produced by p-hacking. The biggest place I think where p-hacking and harking go on is the estimation of conditional average treatment effects. So a lot of people won't find an average effect in their data. an overall effect, so they'll go fishing for differences in subgroups. But any given study has any number of subgroups that you might try to go looking for conditional average treatment effects. Study might have kids from different grades or different cohorts or different ethnic groups or different genders or different social classes. And so a problem occurs when researchers search for conditional average treatment effects by conducting many, many, many comparisons. So if you set that p-value at 0.05, the first thing you got to know is that the power to detect these subgroup effects is pretty low. You've powered your study to find main effects, not subgroup effects. And so now when you're making a lot of these comparisons, unless these comparisons are real, there's or even if there aren't any of these, you have a good chance of finding some conditional average treatment effects just by chance, just by the way p-values work. So again, there are ways to limit p-hacking when talking about conditional average treatment effects. The ethical researcher specifies in advance what Kates are going to be estimated, and further, they adjust their p-values for the fact that they engaged in multiple comparisons, while unethical researchers just show you the things that they discovered and hypothesize after results are known. So in summary, what are we talking about? When you report results, you should report both effect sizes and their confidence intervals and the p-values of those effects. And you should also refrain from using a simple threshold and to determine whether or not a program works, some p-value threshold, and actually report the p-value itself. You should, in your analyses, avoid p-hacking and harking. Pre-register your study. Declare in advance all of the outcomes you are going to analyze and provide those analyses to the reader. Declare in advance what covariates you will or might use in advance, and that way there'll be no surprises. Declare in advance the Kates that you're going to analyze. Now, many people object and think, well, this pre-registration process is too restrictive. I want to explore my data. Pre-registration does not prevent you from doing exploratory analyses. You can say, I'm going to explore effects here and explore these kind of effects here. You can say that in your pre-registration entry. But the point is that when you report those results, you report them as such, and you let readers see the full detail of how those results were arrived at. You don't suppress the results and pretend that you were theorizing about them in advance. Okay, so now we have chosen a sample, we have an inference population, we powered out our study, we report our results after taking into account any attrition that might have gone on. Why is it important to report on service delivery and implementation in your study? First of all, remember that the causal inference literature emphasizes what's called the stable unit treatment value assumption. And it's only reasonable to estimate or interpret the tau average that we get in light of that. And one part of that assumption is there's actually a well-defined treatment being applied to the treatment group and withheld from the control group. In lecture 3, however, we discussed the compliance problem. We know from many studies that treatments often aren't received by the treatment group for a variety of reasons. And for a variety of reasons, it can be the case that members of the control group actually receive the treatment. So we want to know how the treatment was delivered in our study, especially if we're going to move from the intent to treat analysis to the treatment untreated or compliance analysis. It's also the case that we've been describing all along how our logic model says that if I apply the treatment, I should expect that these kinds of implementation processes occur. And we talked in lecture 3 about how we can estimate whether or not implementation mediates the treatment effect. But readers have a right to know, and you yourself should want to know, whether or not, even when the treatment was applied, was it implemented well in the treatment group? And if you're going to estimate average causal mediation effects, you need also to know how much the behaviors and processes in control schools mirrored the implementation processes in treatment schools. So these are reasons theoretically for always studying service delivery and implementation. And as a result, uh, bodies that are setting standards for research reporting, like the consort standards, uh, require that reports include information on treatment delivery and implementation. And that information allows, first of all, any researcher who wishes to replicate your study to do so, because they know what the treatment was and they can compare how the treatment was administered in their study to your description. And it allows the practitioners to actually replicate what you did in your experiment. So the question is how to report on these issues. So first of all, you'll notice that pre-registration always includes a description of the intervention, the target population, the services, the processes and practices defining implementation. Research reports always include a service delivery and implementation check. That is, they provide descriptive data on the extent to which the treatment services were actually delivered to the treatment group and the extent to which implementation processes and behaviors that are expected or define faithful implementation were actually observed in treatment sites. And this is information that you're using as the investigator just to see whether the elements of the program logic model that's driving your research were actually present in treatment sites. And you can use that to interpret findings about program effects, a problem that I discussed at the end of lecture 3 and can be found in the lecture slides. Then, if you have a lot of money and a lot of time and energy, you can actually estimate service delivery and implementation in the control group as well. And doing so will allow you to estimate a treatment on treated effect, as well as to do these average causal mediation kinds of analyses that I discussed. The final issue that I want to talk about is making your data and your statistical analysis code publicly available to others. This is the final step of research transparency and research reporting. So it's increasingly the case in the social sciences and in education that researchers and journals and funding agencies want you to share your data and statistical code. And they want this to be done because it allows others to validate your findings through exact replication on your data, your processes. And, I mean, this is to prevent cheating, but it's also the case that, you might have made an error. It also is used if people want to extend or improve the analyses that you did. They actually need to know what those analyses were, and they need your data to show that their method yields a different result. And it allows you to explore new issues with a data set. So to allow this to happen, researchers are increasingly depositing their data and the analytic scripts in one of many data repositories. And to use these repositories requires you, as a matter of course during your research, to do the following. First, you need to assure a person who is going to access your data that the human subjects have consented to the conditions that you've established for data sharing. And that usually requires you to tell subjects if and how the data will be shared. And in my experience, if you say these data will be shared by researchers who have access and keep the data confidential, human subjects don't balk at that. You need to provide some metadata that describe your data itself, and this will vary by repository. You need to clean the data extensively, de-identify it so no one can identify who the subjects of the study were, and provide a record of the analytic scripts that you use to create analyses and conduct your reported analyses. You'll need to develop code books and repositories of your instruments. Then you'll need to work with the repository to define who can access your data and the conditions of use. And you'll need to preserve the data in a way that can be easily accessed by others. Increasingly, proposals for funding require you to have this kind of dissemination plan. And whenever you publish your reports, you tell people that you have this dissemination plan and they can find your data and scripts at this location. So here's then a summary very quickly of what you should report on when you are reporting the final study report, a report on program impacts. And hopefully, given what I have said in the previous 90 minutes, you will now understand what these elements are. So you begin with some introductory remarks, a conflict of interest, a brief description of your intervention in the research design. You spend time in your final report discussing the sample. You specify the inference population. You specify how you recruited units to your sample, whether it was representative, convenience, whatever. You talk explicitly about how your sample was allocated to treatment and control. You assess the baseline equivalence of the initial sample. You report on study attrition. You describe baseline equivalence of the analytic sample, and then you discuss generalization. You then go to service delivery and you describe the services that actually define treatment and any implementation benchmarks that the intervention has for what constitutes faithful implementation. You then report the service delivery and implementation check so that the reader can be satisfied that, first of all, the treatment was delivered, and second of all, it was implemented well. And then if you have contrasts between treatment and control, you can report them here. Then you move to the contrasts, your pre-specified hypotheses. As we discussed in lecture 3, you'll always report the ITT or intent to treat, the simple difference between those assigned to treatment and those assigned to control in the outcomes. If you've done a pre-specified treatment on treatment effect that you're going to estimate, you can report that. You can report here on pre-specified conditional average treatment effects, emphasis on pre-specified. You can report on pre-specified mediation effects, emphasis on pre-specified. Then, and only then, can you report on exploratory analyses that were signaled but not well described, of course, because they're exploratory in your pre-registration plan. And finally, when you are concluding, you should discuss with the reader your study design and its limitations. You review the findings from your confirmatory analyses, and then you comment on your ability to generalize from your findings from the sample to your inference population. So I'm going to stop with that and open up the Q&A box. So let's take about 25 minutes if we have it to do Q&A. So the Q&A box is now open, and I'm happy to take any questions that you might have. Well, so far I haven't seen any open questions. Having been schooled about wait time, I'm going to wait for a few more minutes to see if anybody has any questions. Very well. I still am not seeing questions. Okay, I have questions beginning to appear, and I'll begin to answer them. So this is a question about, is statistical power the same as the power of efficiency? I just guess I've never heard the term power of efficiency, and so I really can't make an answer to that question. Sorry about that. So the next question is actually about sampling. It says, how can you make sure to think about validity and reliability when sampling? Well, sampling isn't really a question of measurement reliability or measurement validity. So sampling is a matter of attempting to represent a sample so that you can make an inference that's pretty good, not error-ridden, about the population parameter. Whereas validity and reliability are typically issues of measurement. I would say on the validity and reliability question, you certainly don't want to choose samples to study that are not, that the measures that you've chosen to use are not appropriate for. So that's one connection. But but again, I think there's little relationship between measurement. Measurement is not driven by sampling of units so much as it is, a matter of representation and getting a population parameter estimate. So here's a really good question about pre-registration, and it's sort of the question of what's the assurance that somebody says I pre-registered and this is my pre-registration process? What real assurance does that give you that these people weren't p-hacking or engaging in something? And the answer is, you're right. Someone can cheat. You could, for example, uh, fudge misreport, be completely unethical, and provide tables that look like you were following your pre-registration plan, but you fudged the data in some way. That's true. That can always happen. And that they could also fudge the data they put in their repository. And so pre-registration is not a guarantee that really extreme versions of unethical research behavior won't happen. But I can tell you, as an individual who has done pre-registration, it is a disciplining process for you as an ethical investigator. It requires you to think through your design before you engage in it. And it requires you to engage in certain ethical practices. So if you are predisposed to be ethical, then pre-registration is a disciplining factor. And that's really why encourage it. And it's a kind of badge that says, hey, I'm an ethical researcher and I pledge to follow these practices, and this is what I'm trying to do, and this is what I'm going to do, and I did it. So that's really pre-registration. It's not an ironclad guarantee that somebody didn't cheat, but it's a disciplining factor, and I kind of think it was very helpful to me to be that disciplined. More details about pre-registration of a study in medical education. You know, I would consult, if I was in a medical school, I would consult my colleagues. Now, if we are talking about a study being done of the education of physicians, which is not classified or funded so as to be defined as a clinical trial, then I would think that you would either pre-register, say, in the Open Science Registry, or if you're, you know, you want a U.S. audience, or if the audience that you wish to convince that you're an ethical researcher with a pre-registered plan, it you know, believes that the U.S. adds some cachet to your pre-registration. The Registry of Education Effectiveness Studies is another possible place for you to go. You know, the medical education literature is not a field that I am highly familiar with, and it may well be a field that has not yet experienced these pressures for pre-registration. It may not have journals, it may not have funding agencies that really are pressuring people to do that. So that's my answer to that. But you can always use the open science framework. And in fact, that's what a lot of people who are operating in fields where the pre-registration process is not quite as formalized have gone to do this. Let's see. I've got some more questions here. Sometimes we read about self-fulfilling prophecies in research methodology. Right. So I'm not sure, I've not read that term or experienced it, but I'll take a guess at what that means. That you know, the self-fulfilling prophecy of a researcher would be, I speculate or hypothesize or am interested in finding a positive effect of this intervention on outcomes. And what I'm going to do is fish through my data to show that that thing exists. That's the self-fulfilling kind of prophecy. And that's exactly what we are trying to avoid when we have, you know, we're trying to avoid phishing expeditions. We're trying to avoid opaqueness in data analysis. We're trying to avoid, you know, playing with covariates to get the effects. We're trying to avoid reporting positive effects with known defects in, say, sampling and attrition. So that's what the whole emphasis here on open reporting is about. The next question I'm going to address says, is it okay to do principal component analysis at the start of the analysis of the treatment effect, even if it might lead to dropping some variables and a lesser sample size? So, so the answer to that is, if you pre-specify that you are going to do a principal components analysis, and that principal components analysis may lead to missing data, if you do that, you pre-specify that in your plan, then you know, you're not being an unethical researcher. You're saying, I am going to use this procedure to determine which variables I'm going to accept in my principal components analysis. And this may lead to some loss of sample. And so, I'm going to check what the consequences of that loss of sample are for me as I proceed in my analysis. That's the way I would handle that one, basically. So again, the pre-registration does not preclude flexibility in analysis. It simply makes you disciplined and specify, okay, here's what I'm going to do if I encounter this. It's also possible to um, um, file amendments to your pre-registration plan such that you say, okay, I did this analysis, here's what I found, and now this is how I'm proceeding. Okay, so most registries have an amendment process and dates are put in, and okay. The other thing I would say about this principal components analysis, it's a discipline that we use in our research programs. If we're actually using our own sample data, we try to avoid ever having the outcomes in the data set that we are manipulating prior to the outcomes analysis. Okay, so you do this principal components analysis, but you keep the outcomes data out of that data set. We also often don't do that analysis with the treatment group data included. And if possible, we try to do lots of these kinds of tweaking to get the right covariates or building measures in the particular ways on what's known as a remnant sample. That is a sample that looks like our sample, but isn't in our study. And fortunately here in the United States, we're able to do a lot of that because we have large state education databases, or many other studies are available for us that we can use to build these kinds of things. So remnant samples is a protection. Never having the outcomes in your models when you're exploring and building these kinds of measures or checking out covariates, or if you have to use outcome data, try to keep yourself blind to the treatment outcome data. For example, if you're trying to figure out what the best prediction model is for outcomes, don't do it with the outcome data for the treatment and control group in there. You can do that just with the control group. So that's my answer to that. That's a great question. Question here says, some statisticians are veering away from being too p-driven. Is reporting the confidence interval estimate of the treatment effect better than reporting the p-value, and will it solve the problem of p-hacking? Well, I think that you should always report the confidence interval. I have, no objection to reporting p-values. I mean, just like report them, because I'd like to know, given this sample, what's the chance I got this thing different from zero by chance? What's the probability of that? I don't mind that information, as long as I present that information to people so they can interpret it properly, along with the confidence interval of the estimate. And bear in mind that standard errors of estimates are also going to depend on models. And so, I can, another way to sort of p-hack is not just to fiddle with the covariates, but to fiddle with models, overfit them, for example, in ways that shrink the standard error of the estimate from which the confidence interval is based. So no, I mean, the way to solve p-hacking is to be disciplined and make a clear distinction between confirmatory and exploratory, and when engaged in exploratory, to be transparent about it. Let's go to the next question here. So to select sample size, what if we don't follow what's usually recommended by a citation that I am unfamiliar with. But again, the sample size is a judgment call based on how much power you want, based on a bunch of guesses about the effect size you want to detect. And there's no one way or one value that one would pick. And that's because there are so many study designs and so many different considerations. So I wouldn't say that there's any single table or guideline. And whenever you're reading guidelines, I mean, right, the power depends on like variance components, sample size, lots of things. Okay, so it's not a simple problem. This is, can you recommend good sources or journals to find articles about program effectiveness research for further reading? The journal that I think is probably most relevant to attendees here, it's an English language journal published in the United States by the Society for Research on Educational Effectiveness. It's called the Journal of Research on Educational Effectiveness. And it publishes the kinds of studies that I'm talking about, because the reviewers for that journal are rigorous, and the journal is interested in publishing rigorous program effectiveness studies. So that'd be the single one journal I would recommend. Okay, the final question I have in my list is about convenience and purposive sampling as falling under non-probability sampling. How do we ensure that the results of a study based on that kind of sampling are remain good basis for drawing conclusions? Okay, so let's review what we have discussed about this. There are two things to think about when one thinks about the quality of a study. These are often called internal validity and external validity. So much of my lecture series has described internal validity. You are drawing a warranted causal inference about program effects when you can assure the reader that the treatment and control groups are alike on a very, very large, in fact, any possible set of pre-treatment covariates that might affect assignment to treatment and the outcome. That would produce a lack of baseline equivalence. So we've discussed the kinds of problems that arise in that kind of internal validity with different designs. That was what lecture 3 was about. There's debates about whether matching and propensity score stratification are good. There's, anyway, that's the internal validity problem. And so let's go to what is called external validity, which is the problem of generalization that I was discussing today. So a study has, so the question here I take is one mainly of external validity, but let's just be clear. A study could have very good external validity. That is, the study could be based on a representative sample of the inference population of sufficient size that we trust that the sample average treatment effect is a good estimate of the population average treatment effect for the inference population. Okay, so you can have good external validity, but really bad internal validity. Okay, so just because the study has a great sample doesn't mean it was a good study. Conversely, just because a study has is drawn on a convenience sample doesn't mean it doesn't have good internal validity. That is, the effect that was found could have, could be subject to strong internal validity, be judged as a good finding, really a lot of internal validity, a lot of controls going on. My problem with the study is I'm not certain what population it generalizes to. And what I showed you today is how to think about representing the population to which these findings apply by comparing the characteristics of your sample to your inference population. Okay, so I hope that clarifies the issue. There's internal and external validity. The two are actually somewhat orthogonal to one another, and you can have good internal validity and poor external validity, in which case then we probably want to replicate that finding in different populations or different samples to get an inference about our inference population. But if these conditional average treatment effects are large and your sample's idiosyncratic, that treatment effect may not hold up in a different or more representative sample. That's the problem of generalization. But I generally screen first for internal validity and then think about whether I'm willing to generalize to the inference population of interest or whether more studies are needed. So I hope that answers that question. And I think that does. Oh, I see I have more. Okay, let me keep going. I've got the final question here is, would you mind telling me if I can't find the literature review to support the findings? I'm not certain exactly what this question is asking, but I would say that a literature review is used in the following ways. It is used to justify the research questions and review the confirmation status of the findings about those research questions. It's used to justify the hypotheses that you are going to test, and it's generally used, you interpret your results with respect to prior findings and signal whether or not additional research is warranted. That's basically the relationship between the literature review and findings. There's a question here I skipped, which is what formula do you suggest to get sample size of the population? So I'm not exactly sure, but I'll say two things about this question. First is that the question may be suggesting that the size of the population, if you have an extremely large population, this could be referring to what's called sampling fraction. So the trustworthiness of an estimate from a sample to a population is in part dependent on the representativeness of the sample. It's in part dependent on what's called the sampling fraction. So like if I have a tiny fraction of a large population, even if I have a fairly large sample, I may not be representing that sample very well. So you should go for that question, sampling fraction, to any good treatment of sampling statistics and check what they have to say about the issue of sampling fraction. With respect to formulas for computing power, there isn't a single formula, and that's why I send people to those power calculators. Okay, so I'm gonna close down right now, and I want to thank all of you, especially those of you who have attended all 4 lectures. I hope that you are now a bit more familiar with the area of program effectiveness research, and no areas where you need to engage in more study. So with that, I thank you for your attendance, and I am going to turn the screen share off if I can. I'm not exactly certain how I do that. Does anybody know how does anybody know how I can stop my screen? Here, stop share. So I'm now no longer sharing, and I'm going to put myself on mute. Thank you all.
Thank you very much, Professor Dr. Brian. So the next, I would like to invite Ms. Charida Nalong-Sirikun, Manager of Chevron Enjoy Side Project, Chevron Thailand Exploration and Production, to deliver thank you message. Dr. Ms. Charida, please.
Okay, can you hear me well?
Yes, we hear you clearly.
Okay, good morning, good afternoon, and good evening to all fellow participants, Professor Brian Rowan, and all distinguished partners. I speak to you today on behalf of Chevron Corporation and Chevron Thailand, a global energy company who committed in developing human energy by enhancing several kinds of education program investment in this region, including Enjoy Science Project. For those who are unfamiliar with the Chevron Enjoy Science Project, it is one of the Chevron large-scale social investment program in Southeast Asia. The program aims to enhance STEM education in Thailand and the region. One important area of our work is to build capacity of regional researchers to deliver high-quality, evidence-based research that would support effective education programs and policy in Southeast Asia. For this reason, the project and our wonderful partners initiated this Professor Brian Rowan lecture series, and our intention is to see our regional researchers and educators proficient in conducting rigorous, evidence-based research that can support policymakers in making informed decisions on what policy reforms need to be made to improve education outcomes. I'm very glad to see so many researchers and educators joining the lecture series today and the past two sessions. At each lecture, there has been as many as 500 participants from 26 countries, while majorities are from Asia. I am also very delighted to see researchers and educators from other countries taking interest to join us as well. And I hope that the lecture series achieve to strengthen your research capacity, enrich your knowledge on evidence-based research, support your professional development goals, and expand your research network. And I believe that every one of us here today, all researchers and educators, have very important roles to play in improving the quality of education for the younger generation in your respective countries. I therefore encourage you to adopt the research practices learned to conduct research that would help elevate the quality of education in your countries. The Chevron Enjoy Science Project and our partners will be offering education research grants to interested regional researchers. I urge you to take advantage of this opportunity to contribute to your country education development. We would also like to hear from you, from other researchers, on what further support you need to increase your capacity to do high quality research that will be useful for policymakers. In the coming year, the project and our partners will continue to offer more research capacity building opportunities, and I would like to invite you to take part. Before I conclude, I would like to express my heartfelt appreciation to everyone who made this lecture series possible. Special thank you to Professor Brian Rowan for your time and contribution to conducting this lecture series. The knowledge you provided will surely enhance the quality of education research in the region. Also, my deep appreciation goes out to all distinguished partners who collaborate to organize lectures. Thank you to Simeo STEM Ed Center in Thailand, Simeo Rexam, Simeo CPRN, the Teacher Council of Thailand, and Thailand Education Dean's Council. Thank you to Associate Professor Dusadi Intraprasert of Sinakrin Virod University in Thailand, who helped translate the video recordings of the lectures to be used as learning resources for researchers in Thailand. And finally, thank you to all participants for your time, commitment, and meaningful participation. I hope it was a worthwhile experience and that you will join us again on the next occasion. Thank you.
Thank you very much, Kun Charida. So the next is the closing remark. I would like to invite Dr. Phonpan Vaitayakul, Center Director of Simeo STEM Ed, to provide closing remark. Dr. Phonpan, please.
For conducting power. Good evening, ladies and gentlemen. Dr. Rowan's four wonderful lectures have given us a framework for conducting powerful impact evaluations. We are deeply grateful to Dr. Rowan for his thoughtful advice. But now, the next step is up to us, all of us who are members of the ASEAN research community. We must find opportunities to conduct rigorous impact evaluations that will provide policymakers with evidence of what works in critical areas of education in Southeast Asia. Together we need to provide answers to pressing questions such as: how do we improve primary student literacy skills? How do we increase the proportion of students who are competent in basic mathematics? How do we increase the number of students enrolling in STEM fields in higher education? These are among the critical questions facing policymakers in our region, and to answer them and take effective actions to improve education, they need evidence of what works, and it's up to us, the research community, to provide them with that evidence. We say we want evidence to guide policy, but to do that, we must have evidence. Evidence-based reform in education refers to a situation in which policymakers use evidence of effectiveness as a primary criterion for selecting educational programs, products, and practices to be used in our schools. It's not the only criterion. Cost, feasibility, and sustainability are also matter, but effectiveness is a primary criterion. Dr. Rowan has described for us the kind of evidence we need to determine effectiveness of interventions, and now it's up to us to collect it. Evidence of effectiveness comes from rigorous experiments or quasi-experimental studies in which the performance of students who experience experimental intervention is compared over significant periods of time, say a semester or more, to the performance of students who were provided with traditional experiences, the control group, and they must be compared in terms of the gains made on varied measures of achievement. Various research methodologies are used to generate evidence of effectiveness. Distinctive tools for determining the outcomes of effective approaches compared to ordinary practices are experiments or quasi-experiments. In experiments in education, schools, class and teachers, or students are randomly assigned to treatment groups which implement the new approaches, or to control groups which continue usual practices. Quasi experiments are similar, but instead of random assignment, quasi experiments match the treatment schools with control schools based on prior achievement and other factors. Doing such study requires larger samples than many of us are accustomed to using. We need studies with 40 or 50 classrooms or schools, not 5 or 10. This is not the time for a detailed discussion of methods, but it's important to know that the most experiments and quasi-experiments are larger than the studies typically done in the region. These larger studies require larger budgets, so we need to persuade governments and other funding agencies to provide more support for research. I promise you that the Center will be active in seeking funding for research. All of us must join in the effort to persuade funders and policymakers that evidence of effectiveness should be the primary criterion in the adoption of educational products and services. We must help them understand that programs with a strong evidence base that are implemented with fidelity are more likely to produce better outcomes for students than actions based on facts or opinions. Further, using evidence as a basis for program adoption would put education into the cycle of innovation, evaluation, and progressive improvement, which has transformed fields such as medicine, agriculture, and technology. Evidence-based reform is a simple idea. It means engaging in 5 essential activities. First, determining the areas in which improved outcomes are essential to improving the lives of our people. Second, developing and testing new programs, policies, and systems to address deficiencies we observe. Third, finding out what works best in these critical areas at every grade level of education, using well-established experimental and quasi-experimental methods to evaluate promising interventions. Fourth, making educators and policymakers aware of programs and practices that have been found to be effective. And fifth, providing training, resources, and incentives to enable school leaders and teachers to implement these effective programs and practices. These 5 principles underlie policies and practices in many areas that are known for rapid and sustained progress on a large scale. For example, astonishing advances in medicine and public health over the past century are due to evidence-based medicine, where governments have supported research and development of new medicines, techniques, and public health policies, have sponsored rigorous evaluation of these ideas, and have disseminated treatments and policies known to be effective. As a result, national average life expectancies has increased dramatically in China, and in other countries, diseases have been cured. Some, like polio and measles, have almost been eradicated, and preventive practices such as vaccines against smallpox, polio, and COVID-19 have been widely distributed and become standard practices. In agriculture, similar transformations have taken place. In the United States, advances in farming have reduced the cost of food and increased productivity of farms fivefold in the past 50 years. In China, advances in the productivity of rice farming, a tripling of productivity per hectare over the past 50 years, have transformed life, ending the famines that were once common. These and many other advances in agriculture have come about as scientists have developed and tested new seeds, fertilizers, production methods, and insect controls. As effective methods have been tested and proven, they have been disseminated to farmers, making farming more efficient. Smart farming has demonstrated that fewer farmers can feed more people. Until recently, education policy makers did not participate to any major degree in evidence-based practices or policies. Yet education could follow the same path as medicine, agriculture, technology, and engineering, and begin to base its policy and practices on rigorous evidence. Some argue that education is not the same as medicine or agriculture, because a new field or a new seed can readily be replicated, while educational innovations usually require many people to change their behaviors to implement new approaches. Yet these conditions also arise in medicine and agriculture, as when physicians learn new ways to persuade patients to make needed lifestyle changes or to take needed medications. Consider the struggle going on now to persuade people to take COVID vaccinations. Eventually, the evidence will prevail and people will get vaccinated. Education has its own evidence base that has shown positive effects of educational methods, such as tutoring, cooperative learning, and discussion, and these and other research-proven methods could have a profound impact on educational outcomes. But this will not happen unless you take the lead. You must help us persuade policymakers to pay attention to evidence. You must help them understand what warrants to give different kinds of evidence, and you must initiate the studies that will produce the evidence that they need. The quality of our education depends on what you do. The future life chances of our children depends upon what you do. Now is the time for action. I call on all of you to get involved. To this end, I would like to give special thanks to Chevron Corporation for supporting the Chevron CMO policy and research capacity building to strengthen regional STEM education project and making this lecture series possible. I also would like to express my sincere appreciation to the project partners, the CMO Regional Center for Education in Science and Mathematics, or CMO REXAM, the CMO Centers Policy Research Network, or CPRN, the Teachers' Councils of Thailand, and the Thai Councils of Deans of Education. Many thanks go to Associate Professor Dusudi Intraprasad for advising the technical terms for the Thai subtitle in the video of this lecture series, which will be distributed among Thai universities. Lastly, I would like to express my sincere gratitude to Professor Brian Rowan for his dedication and wonderful contribution. Without him, we will not be able to complete this special lecture series on program effectiveness research. Thank you and good night.